and you actually sum total of summer gain minus winter loss, twice summer gain minus winter loss, you can minimize. If you want to select the shape, in winter condition, of course, you would like to say that minimum heat loss occurs. Now, shape actually talks in terms of surface area to volume ratio, right. For a given volume is same. So, surface area, larger the surface area, more will be the losses. I am not going into the algebra part of it, but quickly we can see that this, the amount of heat loss is a function of the outside and inside temperature differences, and it is also function of UA in case of winter, not in Indian scenario actually, but to understand that is better first to understand this. So, larger the surface area through which actually heat loss occurs, well, it will be less efficient. Lesser the surface area through which heat loss occurs, it will be better, right. So, that is the concept actually. I do not think I am going to the algebra part of it. So, minimum UA by V, UA is a representative of amount of heat loss occurring per unit volume, then one would like to minimize in case of winter scenario, right. And there are some algebra available. This is there in a book by this is available in literature actually, Marcus and Morris. They give you a simple formulation with respect to aspect ratio, how simple one, hand calculation based. So, you can find out which is the best orientation from out of say some 5-6 orientation, which are your choices. You can find out which is the best orientation for heating purposes. I do not think I am again going into the algebra part of it, but in case of summer scenario, one got to look into the radiation that would be received, and one would possibly in case of summer scenario, I am skipping some of those mathematical part of it. If you are interested, you can look into Marcus and Morris's book, that would give you the algebra behind it, but I think I will leave that at this stage for here. But in summer condition, you would also like to see that you minimize the amount of orientation goes together with the shape and orientation will go together, because intensity of radiation received would also depend upon the surface area. So, if your external surface area which receives radiation, that will bring in heat, and also if this area is large, it will bring in heat because of the temperature difference in outside and inside. Also, if there is a glass area of the glass, and where direct solar radiation is being received, it might bring in more heat. Now, I must introduce this terminology called solar gain factor. Solar gain factor, right, is the ratio of amount of solar radiation that comes into the glass or transparent surfaces divided by what is incident upon it, right. Obviously, the area is there. So, area of the glass also comes into picture. That is intensity of radiation is watt per meter square, this is a fraction. So, this gives you the amount of radiation that will come in, heat gain that would occur. So, we would like to minimize this as well. So, total radiation heat gain through opaque surface as well as transparent surface plus the heat gain due to temperature differences, that one would like to minimize in case of summer. So, choose the best shape and orientation. Now, that would be governed by area and area of the glass and area of opaque surfaces altogether. This area corresponds to those area which only receives radiation. This area is the total surface area of external facet, where it is some surface might receive radiation, some may not receive radiation. So, this per unit volume one would like to minimize, For example, the best would have been possibly a sphere whose surface area to volume ratio is least, but then spherical buildings are, it's generally not the common thing to have a spherical building. So, where surface area is least, that would be good, and the mathematical formulation is here. So, surface area receiving radiation, or surface area receiving radiation and surface area receiving radiation and exposed to outside temperature, that per unit volume multiplied by the intensity of radiation received on each of those surface, the glass area multiplied by the intensity of radiation there, this sum total of all the heat input that can occur through the envelope divided by per unit volume, where whichever is least, divided by volume, because area and volumes are related. Whichever is the least, that is the best orientation and shape. So, you might have combinations of orientation and shape. Let us say I might have combinations of 8 orientation, some 8 shapes. I will have 64 cases. From there, by even hand calculation or Excel spreadsheet calculation, I can choose the best when I know this formulae. So, these are there in Marcus and Morris book, the mathematics part of it, which I think I am not going to discuss, because it is a relatively short duration lecture. Now, let us come to glass and fenestration. Glass we know is a poor conductor, usually thickness is low and thermal resistance usually is also low. Coefficient expansion of this order, it is opaque to long wave radiation, that is radiation that is generated from inside. So, does not allow low temperature radiation to go through it, low energy radiation to go through it, while transparent to short wave radiation that comes from the sun. And hence, in greenhouses in higher altitude locations, to preserve the temperature, preserve the plant in winter time, they allow radiation to come in and is covered by glass. Today, of course, there are other transparent or translucent material, which plastics and so on, which can bring in the heat, solar radiation it can bring in, but does not allow it to go out. And that is why you have all kind of greenhouse gas you talk about, because greenhouse gas is supposed to form a layer on top, carbon dioxide, methane, what a vapor. They allow short wave radiation to come through that, but relatively do not allow so much long wave radiation, which is generated by earth or bodies within building or human body, etc., to go out, right. So, glass is one of those kind. Solar gain factor is the ratio of heat admitted to the heat incident, that is what I said, denoted by theta, earlier I denoted them. So, poor conductor, thickness being low, as I said, thermal resistance is high, opaque to long wave radiation, etc., etc. So, this typically something like this, solar gain factor would be something like this, an important property of glass for our purpose. Outside radiation comes in, part of it gets reflected from the surface, from the interface, any interface you will have reflection, and then depending upon there will be refraction here. So, it bends because it is depending upon its density and all that, the ray specular ray change their direction and again it changed its direction. So, there is a refraction not relevant for us, but some of the glass heat is absorbed here, some is transmitted. So, some is transmitted. Now, whatever is absorbed here, it heats up the glass and later on a fraction of it is radiated inside, a fraction of it is radiated outside. So, net thing is solar gain factor, this we call is the amount of fraction transmitted, we call it tau, and the fraction of absorbed one, alpha s, is the fraction that was absorbed, alpha s is the fraction that was absorbed. So, alpha s, a fraction of it, tau plus f alpha s is what is solar gain factor, fraction absorbed and a partial part of it is actually transmitted inside. 1 minus alpha s, 1 minus f into alpha s actually goes out. So, solar gain factor has these effects, some are directly transmitted right away, some are absorbed by the glass and then transmitted later on. So, some glass high, there are some glasses, for example, 100% incident, reflected 7%, transmitted 80% and absorbed is therefore 13%, because 80 plus 7 is 87, 13% is absorbed, out of which 9% goes towards outside, depending upon of course outside temperature, etc., and 4% let us say comes inside, then I will have total admitted 84%. So, solar gain factor is 0.84. This is also function of incident angle and it is function of incident angle, etc., So, we shall see that quickly as much as possible. So, heat absorbing glass let us say, which will 100%, but transmit 45%, reflected 6, but it absorbs now 45 plus 6 means 51, 49% is absorbed, out of which 34% goes outside, 15% is inside. So, total 60%. Obviously, this brings in less heat into the room. So, solar gain factor is lower. So, solar gain factor of the glass can vary, and coating etc., or treatment of the glass can change the solar gain factor. By coating or treatment, solar gain factor of glass can be modified. Various kind of treatment, there are a lot of technologies today available. There are some very intelligent one like photochromatic glasses, and there may be all varieties, even the intelligent one like you press the button and you can change the transmission through the glass, like the one used by in the aircraft Dreamliner. So, you press the button, this Boeing 7, I think it is 787 or whatever it is, you press the button and the transmittivity of the glass changes. So, these are high technology material science that allows for all things to be done. So, various kind of treatment of glass is possible and you can use them in a positive way. So, idea is to allow as much as visible light as possible while filtering out the direct sunlight and heat. So, heat admitted is Q AI theta. Theta is the solar gain factor. It varies with angle of incidence, and typically good old days there are modern glasses. I am sure somebody who talks about, I mean if you go through a course on glass technology, they would tell you that what are the different types of glass, what is the material science and technology advancement that has occurred. But typically you can see some 6 millimeter glass. This is absorption transmittance. If I see, it has got high transmittance in the visible portion, which is around 360 nanometer wavelength to 700 and something nanometer. So it allows lot of transmission occurs in this phase, but it does allow this heat radiation, which is infrared radiation, which we do not see them. For example, if a body is not red hot, but hot, you go close to it, you feel the heat, but you do not see that it is hot actually. It might happen sometime hot utensil you touch, because you do not realize that it is heat, because there is no light coming out of it. So, infrared radiation is that radiation. So, infrared radiation in the sunlight is also fairly high, I mean, and 6 millimeter glass allows a lot of it to come, but beyond that it of course hardly any absorptivity. Now, if you have absorbing glasses, like I said, it can absorb lot, actually cuts down this here a little bit, but here it cuts down significantly in infrared radiations, and thereby heat is not brought in much. Some sort of gold coated, nickel coated glasses, where this has reduced down somewhat, but significantly reduced down those one also. Okay. So, solar gain factor varies with the angle of incidence, part of it is reflected, right. So, when angle of incidence is 0, that is angle between the normal to the glass and the radiation, that is falling almost normally, is high, but when it is nearly 90 degree, that means it is passing, gazing through the almost just passing through the glass surface itself, just going through, there is hardly any absorption or transmission or anything of that kind. So, it varies with the angle of incidence, because the path travelled by the light or heat or the radiation through the glass will vary depending upon angle of incidence. When it is normal, least path is travelled, and when angle increases, angle of incidence increases, path travelled is more. So, you can say reflected, part of it is absorbed, a part of it is actually, and part is transmitted, but a part of this absorbed actually also is transmitted inside. So, this alpha S and part of it, the dotted line shows the solar gain factor, as we have discussed just a little bit earlier. So, typically you can have ordinary float glass, coated glass and so on. So, if you are looking for glass in energy efficient building, look for this kind of properties, and depending upon that you can choose the best glass that you know, right, but that is available to you. All right. I have already talked about this altitude, angle, etc., etc. Now, quickly I will talk about solar gain factor, right. This I have already mentioned to you. So, we can use shading devices. Now, what does shading device done? See, for example, I can have a overhang over the window, right, have a overhang over the window like shown here, such that if sun is here, nothing comes in. If sun is here, then it just goes up to the, it completely, it does not reach anywhere. but if sun is below that, then radiation comes. So, depending upon altitude angle of the sun, portion of the sunlight is blocked. It can completely, I can completely block depending upon orientation of my wall. For example, in southern wall, I can completely block it in summer, because altitude angle of the sun in summer is very high at 12 noon, but in winter it will allow sun to come in. So, this is called horizontal shading device. This is called a horizontal shading device, and we define it in terms of what is called vertical shadow angle, which is nothing but this plane is normal to this, this plane is normal to this vertical plane actually, and in this vertical plane angle made at the tip, this is its projection, right. So, this is what is called vertical shadow angle. So, horizontal shading device is characterized with vertical shadow angle, and similarly I can have vertical shading device. This is horizontal shading device. Yeah, this is what the angle, same angle I am showing, and there is an equation. I do not think I will go into that equation at the moment. The algebra part of it is being talked about. Simply the geometry 10 epsilon. Epsilon is what is called vertical shadow angle is HW by AB. So, 10 gamma is the wall solar azimuth. It can be related to that. Sec delta is equals to AC by AB. So, one can actually geometrically relate it. So, this is the horizontal shading device. So, 10 epsilon is 10 gamma plus sec delta, right. I do not think I will go into this now, algebra part of it. Similarly, I can have vertical shading devices, which will block sun on this side can block. For example, east facing wall, the sun moves. So, early in the morning the sun ray will be falling, but I do not want that sun, let us say. So, I can block it by a vertical shading device. Similarly, afternoon I do not want, so west facing wall, so I can block it, right. So, vertical shading device have what is called horizontal, they are characterized by horizontal shadow angle. Again, this is same as wall solar azimuth. The geometry, from geometry you can define them and find out. So, this is actually same as wall solar azimuth. The derivation of this, I think I am not going to go in this particular lecture, but one can look into this.